So you're trying to classify, how many groups do we have?
Two.
Two groups. How many features do we have? Why is it two? Because you have x and then y. Okay? So for each data, what do you have? You have the x value and the y value, right? If you had three features, you would need a three-dimensional graph, then it will be harder. And if you have more features, then it will be impossible to graph. You'll have to just graph by pairs. Okay? So let's assume this simple situation. We're trying to classify between these two. And then you want to come up with a way to classify using decision trees. And let me show you one. So for now, let me first present you with a decision tree without talking about how you could build one. Right? So I think a nice thing to do would be, let's say this is 1, and let's say this is 3. Okay, and then let's say this is 2. Okay. Then the decision tree that can classify this would be like, so let's say circle is group 0 and X is group 1. Okay. So I would first look at the X value and ask the question, is X less than 1? Okay. Now if X is less than 1, what's your conclusion?
That it belongs to group 0.
0, yeah. Okay? What if it's not? Then you'll still need to have another criteria, right? What should I pick?
We got on 1, between 1 to 3.
Right. So I need to, well, I know that anything on this side is bigger than 1, so I don't have to talk about X being bigger than 1, right? All we need is to talk about 3. So what do I say? X less than 3. If it's true, then it must be, well, we don't know. If it's false, what do we know?
It's 0.
It's 0. Okay. So if it's above, then it's 0. Okay? Now notice that I'm placing yes on the left side and no on the right side. That's a convention. Okay? You could also, and often people would draw these arrows so that it's easier to see what's going on. Some trees will have T and F, true or false, like this. But if you follow the convention that you always put the true on the left side and then false on the right side, yeah, so that then this is a tree drawing. And now, finally, what are we left? These are the guys which are between 1 and 3, right? So here, what should I say? What's the criteria?
X bigger than 1.
No. What's the criteria? No, look at the data. What do we have? X less than 1 is this part, and this one. And X less than 3 is these two, and then this is what we have, right? Yeah.
X bigger than 1.
Y is less than.
Y is less than 2. It's not X, it's Y. Because we now have to use this feature. Okay? We've used up all the X feature. Now we have to use the Y feature. So Y is less than 2. What does this one say?
X.
X. So it's group 1. Okay? And then this one?
0.
0. Okay? So that's a decision tree. All right. So this one here is what's called the root node. And these are called branches, because that's where they branch out to different cases, right? And then the last one, these are called leaves, or leaf nodes. I guess that's like leaf nodes. So leaf nodes are where you end up with a conclusion, right? Now, one interesting thing about this decision tree is that it's in some sense superior to the other one. What was that? The support vector machines or logistic linear regression, because this is not linearly separable. See, logistic regression or support vector machines, at its most primitive form, it can only divide sets by a straight line, right? But this is not linearly separable. So in both cases, for logistic regression or support vector machines, you need to have the kernel trick, which is to add an extra variable where you say you put the distance from the origin as an extra variable, so that now as this one
That's it.
Okay, so where was I? Oh, yeah. So for logistic regression and support vector machines, to be able to classify something like this, you need to add a third axis where you calculate something like distance from the origin, and then now these things are in the space and they're more apart, then they might be linearly separable. Yeah, something like that. You have to do something called kernel trick. Or you can also take the distance not from the origin but from the center. Okay, that's probably better. So if you take the distance from the center, these are closer to the center, and these are further away. So if you make that as your third axis, then these are higher up, whereas this is closer to the bottom, so they're linearly separable after doing that. Yes?
So for the part of the decision tree,
Mm-hmm.
just like in the very beginning,
Mm-hmm.
when it's less than 1, how do you classify between the values that are above 2 and below 2, just from the first part? I don't see how like the top less than 1, greater than.
This one only classifies between this one to that one.
Oh, okay.
Yeah. So everything here will be following this node.
So then, are we using this to separate x from 0, like the O's?
Yeah, it's either 0 or maybe I should have done 0 and x. It's either 0 or x, right? So it could be, for example, if you had like people with heart disease with something like cholesterol level and also something like hypertension. You would have 2 different feature sets, and you have to figure out if this person has heart disease or not. Yeah.
So then we don't care like the difference between like the less than 2 or greater than 2.
It's
We're just trying to
eventually
separate
calculated
out
here,
the
isn't it?
zeros.
It's here. Y is less than 2 or bigger than 2. At some point, it does get used.
Yeah.
Some indicators are just evident. If it meets this, then definitely this person has heart disease or something like that. Definitely it's group
Overall,
O.
like, we're just trying to get the x's separated from zeros? Or
That's
from-
always what a classification problem does.
Okay.
You always look for ways to separate the x's from you have 2 groups or 3 groups that you just want to classify. Yeah. Is that okay?
Yeah.
Yeah.
If
Yes.
you have like x between the two zeros in the middle,
Uh-huh.
do we draw another line to separate between them? Like between the two O's on the middle, on top of two.
Top of 2 and what?
Between the two zeros, and you have like x over there. Right after.
This one?
No, above.
This one?
On the left, no.
This one?
Between those two, if you have x, no.
These?
No, between the two zeros,
2 zeros.
yeah, you have an x between them.
If you have an x between them.
Yeah. Do we draw another line to?
Oh, I see. So, okay, that's an interesting question, right? So the thing is, this is rather nice, right? It's easy to like draw vertical and horizontal lines to eventually separate the 2 groups. But what if you have something like this? Now what do? Then after doing this, right? You will need to do another one. So I said if it's above 2, it's O, but no, it's not, right? You'll have to do this again. And actually, unfortunately, you will have to do it 3 times, right? So you will have to, so there'll be something like, if I say this is like 2.5 and 2.7, that will be like 2.5, x less than 2.5, it will be O.
And then x is less than 2.7.
2.7, it will be x, and then this will be O, right? So you'll have this. Yeah. Oh, that's a really important question because, so while it's true that you can use the decision tree to classify things that are not linearly separable, the decision trees can easily get very complicated. And another problem is it's going to depend a lot on the data that you're going to train with. Right? See, just adding this single data point forces you to have 2 more branching nodes. Right? So it's not good because now you have a much more complicated one, and then guess what? If you have a new data set for the testing data, if you bring one that's not used for training, it's very easy to get something like here or there, and it will be misclassified as soon as you do it. So one thing that you have to be able to do for decision trees is you have to have some criteria to limit your decision tree from overfitting. So this is like overfitting to the training data. Okay. So the way you overfit the data is you can have a limit on the number of branching points, okay, or levels. Okay. Let's say we can't have more than 4 branching points, or more than 3 branching nodes. Okay. So if you do that, then at this point, what you do is, well, I wish I could put more branching nodes here, but I'm not allowed to, because we said we were going to limit to 3 branching nodes. So we're just going to stop here. And if you stop here and you have this, what you say is, well, I can't put any more branching to classify these, so what do? We just have to say this is O with 66.6% accuracy, 66.7% accuracy. Yes?
So would that be the case with like any outliers as well?
Yeah, outliers would do that. You would be forced to, be forced to draw a leaf node here, despite the fact that you don't have a pure state. Okay, and then So that's one. You can limit the number of branching nodes. Another way you can do this is you can also limit the number of size of a leaf node. So see, this leaf node has 3 examples, right? You can limit it to 3. Okay. If you have to branch and in your training set you have less than 3, you stop. You don't branch anymore, and then again you write down the leaf node by writing down the highest number. Okay? All right. Yeah, so decision trees, in theory, decision trees are very nice, but in practice, decision trees are very bad. The overfitting problem is the worst among every machine learning methods that we learned. Now, still, you might wonder then, why do we learn this at all? Well, what people do is they build forest out of the trees, decision trees, so I'll talk about that today as well. And if you build forests from the trees, then they become a lot better. Okay. So we'll talk about random forest later. Okay, so I gave you the idea of what a decision tree is, but then still, how do you train one? I mean, you're not going to be writing these rules by hand. That would be terrible. You don't want to do that. You should let the computer decide what the branching point should be. Okay, and that's when you use the Gini impurity index or the total total entropy. Okay. All right. So let's talk about how to train a decision tree. So the machine, for us humans, it's kind of evident that these are the preferred lines to divide. But if you're a machine and you can't really make that conclusion just by viewing the data, you kind of have to do this as if you're a blind person running up the alley, right? Or walking up the alley. So what you do is, let me see, how many data points we have? Let's keep that one there so we kind of know what's going on. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 data points. That's what we have. Right? And if you project everything down to the x, that means you have 13 values, right? And every point in between will be a possible place of division, right? So you have 12 possible points of division, right? So what you do is you just keep like dividing, like this or this. Just try doing that for everything. Now, since it's impossible to do all 12, let's just compare these two possible divisions. Okay? And then let's see why this one is superior to this other one. Right? Or is it? Maybe. I'm not so sure. That's kind of dangerous. So let me make this one. So that's still the same. Oh, that's good. Okay. So option. Let's just call this A and B. Okay. Let's think about why A is a better point for splitting than B. Okay? So we're going to compute the Gini coefficient for A. Let's do this. So for Gini coefficient, Gini index for A, you have actually you've split it into one part and another part. So you actually have a Gini index for this left part and a Gini index for the right part. Okay? And at the end of the day, you have to compute their weighted average of the Gini index to get an overall Gini index for the entire A. Okay? So let's call this A1. So we're going to say Gini index for A1 and Gini index for A2. So when A is being used to divide, you have one part and another part. Okay, and then we're going to take the weighted average. Remember, the total number of items is 13. So this is 3 out of 13, and then this A2 is this much, which is 10 out of 13. So we're going to compute it like that. I didn't bring my calculator, so you guys will have to help me here, okay? So what is Gini index for A1? Well, there's only one group, right? So what is that? You have only one probability, right? With P equals to 1, right? So what's the Gini impurity index? Huh? 0, right? Okay. What is the Gini impurity index for A2? Well, you have this many X's and this many O's. Let's count them X's. You have 6 X's. 6 out of 10, right? So that's one probability, right? The other probability is 4 out of 10. And the formula for Gini index is you do 6 over 10, 1 minus 6 over 10, right? Plus 4 over 10, 1 minus 4 over 10. Remember, the formula is summation of pi times 1 minus pi. Okay? Now, we only have 2 groups here, so the Gini index will always look like this. If you have 3 groups, then you'll have sum of 3 terms, and they'll look much more complicated. Yeah. But when you just have 2 groups, it's these numbers will always come out to be the same thing. So it will be 0.24 times 2 is 0.48. Okay. And now G of A is, this one I need a calculator, so please help me out here. What's 10 times 0.48 divided by 13? What do you get? You get
369.
0.369. Okay. So that's the Gini index, the overall Gini index if you cut at A, right? Okay, now let's do the same thing. G of B. You know, I think this is a good problem for you to try. Can you try G of B? It's a weighted average, so what number should I put? For B1, what do I put? 1, 2, 3, 4, 5, 6. So what do we do? 6 out of 13 for the Gini impurity of B1, okay? Plus this other guy. 1, 2, 3, 4, 5, 6, 7. 7 out of 13. Gini index of the second one. Okay, what's the Gini index of B1?
6 out of 13 times.
No, it's not. It's, how many is this one? It's 6. So you have 4 out of 6 for one of the probability. And you have 2 out of 6 for the other probability, right? And then you do 1 minus 4/6 plus 1 minus 2/6. 2 over 6 times 1 minus 2/6. So what's that? That's 2/3 times 1/3.
2. Plus.
4 ninths. Okay? Right, so that's 1/3, 2/3, 2 ninths. Yeah,
Yeah.
4 ninths. Okay.
Yeah.
All right. So, that's GB1. But then, what's GB2? this part.
3 out of 7
3 out of 7 times 1 minus 3 out of 7
plus
plus 4 out of 7, 1 minus 4 out of 7. Okay. So what's that? 24 over 7. Okay. All right, so now we can go back and plug in those two numbers. So times 4 ninths times 24 out of 7. So they cancel. Oh, sorry, this is 49.
yeah.
So after 7 divided by 40, it'll still be this. And then this will be 3 and this will be 2. Okay, well, what do you get? So what is 8 divided by 39? 8 over 39. And what's 24 divided by 91? What's this value?
0.468.
0.468? Okay. Okay. So, which one wins? The lower the impurity index is, more pure you've separated. So which one do you like better?
GB.
No. You like this better.
Oh, GA.
GA. Yeah. You like the A as the cut point better than B because this one has a lower impurity index. Okay. You take a point to, as a cutoff and then you look at it and just keep figuring out the Gini. Well, it took a lot of time, but for a computer, that's a very easy thing to do, right? So you would just start scanning from left to right and compute all the Gini impurity index and figure out the cut point that's smallest, right? And then you do the same thing as you go this way, just like that. Okay.
So for the computer, you're just feeding it the graph, and then you're running the Gini
The
index.
feature data. So you have feature X and feature Y, and then you just go through all the feature X's. You should first order them so you know where the cut point should be, and then you start like cutting things off into two separate groups, and then figure out the Gini coefficient, and then Gini index, and then you figure out the one that has the lowest. Okay. Yes.
So when you're doing your cut points, would you then want to start your next cut point where the last one left off?
What's the question again?
When you're like finding multiple cut points
Uh-huh.
on one axis,
Uh-huh.
would you always want to start at 0 again, or do you want to start at your last cut point?
No, it's like there are 12 possible cut points because there are 13 data points, right? You just try all of them.
Oh.
Yeah, you just have 12 cut points. And also there will be 12 cut points in the Y. These are so close there, it's hard to visualize, but there will be 12. And then you also do it here. So you do a total of 24 cut points, and you compute the Gini index for everything. And then once you're done, you choose the one that has the smallest value of Gini index. Now, you could also do the same thing, which is less easy to compute, but you can also use the total entropy. So let's see, the total entropy of A could be written as the entropy of each. So let me rewrite this. So now we can use the entropy calculation. So we can do the same thing, but the criteria is now, instead of using the Gini index, we can use the entropy. Same idea. Usually you use H for entropy. Same idea. You calculate the entropy for each case, and then you take the weighted average, and then you just look for the smallest one. Okay. Now, I've given you the formula for the entropy, which is it's the negative of summation of pi ln of pi. And I explained last time that this measures the average information content of something. Okay. And again, the idea is same. You want the lowest entropy. Okay. So you want to figure out the one with the lowest entropy because, again, see, if you add these, you will again see that if you have values that are, let me see. Yeah, so if you plug in 0 here, it becomes 0, right? Also, when pi is close to 1, ln of 1 is 0, right? So this again gives you a value close to 0 if the values themselves are close to 0. Okay. So the role that this plays is very similar to the Gini impurity index. It's harder to understand what it means. I tried to explain last time, but at the end of the day, if you use entropy to make a decision tree, it won't be the same, but it will be pretty similar if you instead use the Gini index. Okay? So if I were to use this one, well, this will be, you have one probability which is 1, so ln of 1 is 0, so this will be 0, same story as before. So you just get 10 over 13 of h of a2. In this case, you have two probabilities. One is 6 out of 10, negative 6 over 10, ln of 6 over 10, minus 4 over 10, ln of 4 over 10. So you can do this computation, and you can do the same thing for the cut point B, and then you can compare them, and you just use the one with the lowest entropy. Yeah. So similar idea.
So what is the advantage and disadvantage of using entropy? They're very similar.
They're very similar.
Is it just like a thing with the computer hardware that entropy it's a little more hard to calculate with the ln?
Entropy has a probabilistic meaning. So we've been using entropy a lot. The loss function for logistic regression was also entropy, somewhat like an entropy. So if you're trying to classify with probability in mind, then it will be more correct. Yeah. But that's all I can say.
Okay.
All right, so that's how you build a decision tree. Yes.
Wait, why was HA1 0?
Oh, because this is just only P.
Right. Okay.
P1. P1 equals to 1. That's it, right?
Okay.
So this summation is a single summation with 1 times ln of 1. What was ln of 1?
0.
0. So 0. All right. So you just so this kind of explains a way to generate decision trees automatically from your training data. Okay. Now, adding to this, let me just talk about 3 popular ones. So there's ID3 and C4.5, and these are decision trees that use the entropy loss function. And then there is the CART. This is the one that uses the Gini loss function. Originally, the very first algorithm that was invented was ID3. And ID3 allowed your branches to have 3 branching. So you might have a single thing, and you you can have 3 different branches coming out. And that's possible if your data is categorical only. So, for example, you might have size feature, where instead of measured as inches, you might have small, medium, and large. Okay, so you might have depending on the small, medium, large, you might have 3 different branching. So that kind of branching would be ID3. But the limitation was that this algorithm, you weren't able to use continuous data. C4.5 used this kind of idea to allow continuous data. And then later CART was developed using the Gini loss function rather than an entropy. But they're mostly similar.
Can you use a CART with entropy? Entropy loss?
I don't know. I guess you could. Yeah, there's.
They're very similar.
Yeah. Yeah, you can. The thing about CART is that this is classification and regression tree. Yeah, that's what CART means. And so you can use the CART to actually do regression. Regression by a tree often does this. You would so regression means you're trying to predict a continuous value, right? So instead of classification, what you do is you start branching and branching. At the leaf node, what you do is you take the median of all the samples that you have in the test one, and that single value will be the predicted value for the everything. So if you use CART to make a prediction of continuous values, what it's going to do is if you had the single feature, it would be something like this. Something like this. Okay? So you'll have piecewise constants functions generated by CART. So obviously this is not that good, but one nice thing about this is that you could even approximate things that are a lot linear. So if you had multilinear regression, if your data set is like this, then multilinear regression will do that, and these will be very misleading. Whereas if you use CART, then it's kind of rough, but still it does a good job, even being able to follow things when it's coming. So these are decision trees, right? Okay, so as we have seen, the decision trees are very sensitive to your training data as outliers. So it often does a great job on your training data, and then when you apply it for your test data, it just miserably fails. Okay, and you know what that feels like, right? Yeah, all of you are trying to do this homework number 3, making your own digits, and your support vector classifier was performing like something like 90% on the training data, even on the test data on the similar set. But when you made your own letter of 4 or 5 or whatever, you feed it in, and it miserably fails to figure out what it is. So this problem of overfitting to your given data is a very important one. You want to avoid it. And a way to do that is called random forest. So let me try to explain what it is. So let's start with similar. I shouldn't have erased this. Let's say you have this data point, this time 9 points, just to make it simple. So it requires two ideas. One is you do something called the bootstrapping. And what it does is it randomly selects points from your given training data. So let's say I pick this one by random, I put it here, okay? And then I pick this one by random, I put it here, okay? And then you do it for 9 times. You do this 9 times. Now that doesn't make sense, because if you randomly select 9 things, wouldn't you get the same thing? But the answer is no, because you're allowed to repeat. So this point might be the next choice again. So this might be chosen twice, right? And you might have this one. This one could be chosen twice, and then X, and then this one could be chosen, let me see, 2, 2, 4, 4. Yeah, this could be, let's just say this is chosen 3 times, whatever. Okay. Something like this. So you do this, all right? And then let's also assume that these data sets that we have doesn't just have 2 features. We just graphed 2 features, but it has like 10 different features. If you have 10 features, which will require 10-dimensional graph to actually visualize, which we can't. That's why we just pick 2 features to graph. But let's say we have 10 features. Then what you do is you limit yourself to just 3 features. 3 random features. So 2 things are done randomly. You pick points randomly with repetition. You pick features randomly with repetition. Of course, these are parameters that you have to, this would be a parameter that you have to determine whether you want 3 features, 3 random features, or 4 random features. We don't know which is better, so those you have to tweak. So you do this, and from this you build a tree. Build a tree, or grow a tree. That sounds better, right? Grow a tree. So that's called bootstrapping. But the thing is, you can do this many, many times, right? So now you can build a forest. You can take another bootstrap sample, another random feature sample, grow a tree. Okay? You pick another one, grow a tree. Okay? You keep doing that. Okay? Then you have a tree here. Our trees are upside down. So you might have like a bunch of different trees, tree 1, tree 2, tree 3. You have many, okay? And that's also depending on how many features that you choose. Like if you have 10 features and you're choosing 3, you probably have to make sure that all the features are represented by some tree. So you need to have enough number of trees. Okay, so you have this many. How would you use this forest to determine, do the classification?
The one that has the lowest Gini index?
No. You use the Gini index to train each tree. Okay? So that's being used. But once these trees are given, these can make their own decision. So let's say here comes a unknown item with many, many features, right? And then you go through the first tree, it says, oh, this guy's a O. You send it to the second tree and say, oh, this guy's an X. They would come up with different answers because they're trained with different data and different features, right? So you would have different conclusions coming from different trees. Now, what do you conclude then if you have different conclusions? Huh?
We have to see if the predicted is the actual correct value.
No, we don't know. Yes.
The biggest tree is
Huh?
the biggest tree is the most precise, or the most accurate.
No, no. Okay, well, maybe.
Do we weight them like if you have more zeros or more x based on that?
Yeah. If there are more O's than X's, then O wins. So you aggregate the conclusion, right? And that process is called bagging. Right? So bootstrapping and then bootstrapping the data and making up different conclusions, and then taking their aggregated conclusion as your final conclusion, that process is called bagging. Okay. Now, having different predictors or classifiers and putting them together to come up with a single answer, that's called boosting. Okay, so you can say that bagging is like bootstrapping plus boosting. Okay, yeah. But boosting doesn't have to be among the same type of algorithms. You might be able to do boosting from different algorithms. So, for example, I asked you to do this machine learning project using 2 different algorithms to predict the same thing, right? So if you have algorithm 1 and algorithm 2, you can just take their average, or if you have 3, you can figure out what the majority conclusion is and follow that one. Okay? So that could be boosting. Okay? You can use boosting to have stronger results, right? So that's random forest. There are a few additional things that you could discuss. There's something called out of bag element. And that one is like when you do bootstrapping, this is not chosen, this is not chosen, and this is not chosen. So these 3 items are what's called the out-of-bag element. And these are important in figuring out how accurate your decision tree is. You take an out-of-bag element, and you can put it back into the tree that's being trained. And if it correctly identifies the out-of-bag element, that's good. You can also look at the accuracy of the out-of-bag element for each of them. And then that can tell you the weakness of the tree. And you can also take weighted average. If you know the weakness of a tree, then you can also take weighted averages using the weakness. That could be another way to aggregate. That's all.
Thank you.